All right, we are going to now study graph data structure, which is a topic in data structure subject, which comes under data structure subject. So basically we'll be learning the most important thing that we have to learn in graphs. So let's start, and we'll be trying to complete the whole graph section in under half an hour, okay, so that it does not take much time and you get the concepts very easily. So just give me a second. Okay, so graph, this is the topic. So what are the very important topics that we need to learn in order to pass the exam? So firstly we need to learn about the representation, like how do we represent the graph. The second thing that we need to learn is the traversal. Like for any data structure, the most important thing is how do you traverse that data structures. Like if we talk about an array, we need to know how are we going to traverse this array. If you want to search something, what do you need to do? You need to know how to traverse this array. If you want to find the largest element, what do you want to do? You want to traverse the array. Okay, so that is what I'm trying to say here. So in order to traverse, the most important algorithm that comes to our mind is BFS and DFS. I'll tell you the full form and everything in just a second after teaching representation. The third thing that we are going to learn in this chapter is the shortest path algorithm. Okay, so this is the third thing that we need to learn in this chapter. In shortest path we just have to learn one thing, which is disjectras. Okay, disjectras algorithm is the only thing that we have to learn, that is only there in our syllabus. The fourth thing that we'll be learning is Prim's algorithm. Okay, Prim's algo. Now there is a thing called MST in graphs. MST, I'll tell you everything, like what is MST, what do you have to learn in MST, why MST, and how do you find an MST, what is the algo to find MST. But for now just listen, there is a thing in MST. In MST we basically have two very important algorithm which helps us to make MST. What are those two algorithms? The first one is Prim's, M, not Prim's, and the second one is Kruskal's. In order to write Kruskal's, I'm saying in order to write the algorithm of Kruskal's, you need to know DSU, which is disjoint set union. And believe it that DSU is little bit tough to understand. Okay, so we are going to learn Prim's only, not Kruskal. And if the question comes up in exam, like write a short note on MST or anything, you can go on with Prim's. If the question comes up in exam that write a short note on Kruskal's algorithm, you can write Prim's algorithm, you will get some marks. Okay, so you will just write Prim's algorithm. So our target is going to be like completing this chapter in under 40 minutes, and then the next lecture will complete the sorting algorithms. Okay, so we just have 40 minutes and I successfully wasted 3.5 minutes. So let's just start. So the first thing, representation. So the first thing that might come up in your brain is what actually is a graph. Okay, so suppose I have something like this, 1 2 3 4 and then a 5. Okay, so here as you can see, each element is related to is somehow related to other element, and that relation is relation is denoted by edges. Okay, here as you can see, what do we have? We have a node inside of which we have value of that node. After that we have edge. So if 1 is connected to 2, that means there is some relation in between 1 and 2. Now the question that might come up in your brain is, do we always need a connection in order to make a graph? So let me just take another example. What I'm trying to say here is Suppose I have a graph like 0, 1, 2, and then I have another graph which is 3 and 4. Okay, so this is a graph, like this is a graph, there is also a graph. I ask you a question, is this a graph? Is this overall is a graph? Wait, just I'm saying, is this a graph? You will say no, this is not a graph, because there is no node that is connecting the nodes of this graph to this graph. But that's not true, this is also a graph. So here is when the definition of graphs really gets deeper. What do we actually mean by graph? So suppose if I say there is a node A, there is a node B, if there is an edge in between A and B, that means there is a road existing between A and B. And then suppose there is a node C and there is no edge from A to C, and there is also no edge from B to C. That means there is no road between A and C, and A and B. Sorry, not A and B, but C and B. C and B. Okay. So suppose you want to design an application where what you have to do is you have to go and search, is there a road? If there is a road, assign a bus to it, like there will be a bus that will take us from A to B. Because there is no road that exists between A and C, then that's the reason why you have to assign a flight from A to C, because there is no road, so bus can't go, so you need to assign a flight from A to C. Similarly for B to C also, you need to assign a flight. So as you can see here, the relation here was identified by this edge, and then this edge meant that there is a road, but there was also a relation. If there is no road, that means there is a flight. So in order to do that, we did not make any node, like we did not make any edge. You know what I'm trying to say here. Again, please understand, A to B, there is a edge. When there is a edge, there is a road, right? And when there is no edge, there is a flight. So this is also a relation, na? Understand this. This is also relation only, na? Ki if there is no edge, then there will be a flight. So this is also relation. So if you see, this is also a graph. This is also a graph, because A is connected to C. You know, connection does not means there needs to be edge. There can be a invisible edge. Invisible edge, sorry, not invisible. Invisible edge. So invisible edge basically means that there is a flight. This is not true every time. I just took an example that if there is a edge there, that means there is a road. If there is not any edge, that means there is no road. So but in this example, you can say one thing, which is कि there are two connected components in this graph. Okay, what do I mean by that? The first component is A and B. See, AB is first connected component, and C is second connected component. Now you will say, okay, A to B, I understand it is a connected component. How C is a connected component? So in order to understand that, you can see that C is connected to C only. So in the connection is like that, one element is always connected. Okay, like if you understand this, good. If you don't understand this, just remember it. Like one element is always considered as a connected component. So how many connected component is there? This is the first one and this is the second one. So there are two connected component in a single graph for this example. Okay, so now you understood what is a connected and what is a disconnected graph. Now there is one more thing that we need to understand in classification of graphs, which was our first topic, which I decided not to teach, but I don't know why am I teaching this. Okay. 1 is connected to 2, 2 is connected to 3, 3 is connected to 4, and 4 is connected to 5. Now suppose you want to go to you want to go to 5 from 4. No, okay, you want to go to 4 from 5. Okay, so suppose the length in between 5 and 1 is 2, the length in between 1 and 2 is 1, the length in between 2 and 4 is 3, the length in between 2 and 3 is 6. Okay, this is just an example that we are trying to take here. Suppose I ask you what is the length in between 5 and 6. No, not 5 and 6, but 5 and 4. So you will say 2 plus 1 3 plus 3 6. Okay, and what is the length in between 5 and 3? You will say very easily that the length is 2 plus 1 plus 6. How much it is? 9. So what is helping you to determine the distance here? The weights. Weight is helping you to determine the distance. Okay, so these weights could be anything, you know, these weights could be anything. I'm just saying here that here the weight meant distance between two particular nodes, but the weight could mean anything. Like it does not need to like always mean distance. Okay, so this was weighted graph. What about an unweighted graph, like non-weighted graph? 1 2 3 4 and then a 5. Now here what is the distance in between 5 and 4? You can very easily say the distance in between 5 and 4 is 3, because when there is not any weight assigned to each edge, then you can say that the weight 1 is always there. You know, when not assigned, that means 1 is there. When assigned, that means whatever the value is given, that is the weight. Got it? I just hope that I did not over explain this thing here. So now let's move on to our next topic, which is representation. Okay, like how do we represent a graph? Suppose we have a graph 1 2 3 4 and 5. So there are two types of representation: list representation, and the second is matrix representation. The list representation is O of n, the matrix representation is O of n square. Now what is O of n, what is O of n square? If you got it, very good. If you did not get it, no problem, just no problem. Like this is not important that list representation is O of n. It could be O of n square also sometime, depends on the type of list that you are taking, but you don't need to understand this. If you like kind of like remember it, then you like can write it in exam that the space complexity taken by list is O of n generally. Always write generally there, but matrix always takes O of n square, like for a 2D graph, you know, not for a 2D graph, like for always, like it will take a O of n square. Okay, how do we represent this graph now? So you can say that one's neighbor is 2 and 5. Correct? One's neighbor is 2 and 5. What about 2? Who are the neighbors of 2? 2 has a neighbor 1, 2 has a neighbor 3, and 2 has a neighbor 4. Correct? What about 3? 3 has a neighbor 2. As you can see here, 3 has a neighbor 2. What about 4? 4 has a neighbor 2 only. What about 5? 5 has a neighbor 1 only. This is how you do this list representation. Okay, you got it now? How are we actually going this doing this list representation? If you got it, very good. This was our first topic over. Representation over. Now you will say you do not teach matrix representation. That's not important. Like nobody will tell you to like do matrix representation or anything like that. Like list representation is always better. There are many good coders who don't know what matrix representation actually is, so you don't need to go in detail. But one more thing, if you have heard about this incidence matrix or this adjacency matrix in discrete mathematics is also a subject which you might have studied. If you have heard about these two topics, then you know about matrix representation basically. Okay, you can write that same thing in data structures also. You'll get the marks. Now let us just shift our focus to the traversal, which are very important. Traversal. So I just hope that you guys are making note if you are studying from me. I don't know how many of you are actually studying, but no problem, like I'm just making a video. If you find it helpful, you can study. Okay, so the next thing that we are going to do is traversal. Okay, so let's take a simple graph and we are going to traverse in that graph. So 1 2 3 4 and then a 5. Okay, this is the graph that we are taking. 1 2 3 4 5. Here we are going to represent its adjacency list. So 1's neighbor are 2 and 5, 2's neighbor are 1 3 4, then again 3's neighbor are 2, 4 neighbor are 2 2, and 5's neighbor is 1. Correct? The adjacency list, you get it what I'm trying to say here. Now how are we actually going to traverse? So let me just first tell you one thing, what actually is the output of BFS. And one more thing, like what is the full form of BFS? The full form of BFS is breadth first search. This is the full form of BFS. Okay, so breadth first search. Breadth first search means go to this level, write what you get. You get 1, you write it. Go to this level, write what you get. You get 2 and 5. Now you might say that why not 5 and then 2? You can do that too also, like 1 5 2, you can write that, it's not wrong. And then you come here, you get 3 and 4. You can write 4 and 3 again, like that's correct. This is the correct output of BFS. So you now know how are we actually going to write the output of BFS. But how is the computer going to know what is the output of BFS? Okay, so this phone has a very small screen, so it's causing a little bit of problem to me, to be honest. Wait. Here I'll again have to draw a graph. Do one thing, you might be having a note this graph, okay, that I'm drawing here. 1 2 3 4 5. Okay, the first step is take a Q and push the neighbor. Take a Q and push the neighbor. Okay, so the first thing that you'll always do is make this adjacency list. Okay, make this adjacency list and then take a Q and push, not push the neighbor, but push the source. Push the source. Source. Okay, so what is the source? Source is 1. Okay, source node, this node is known as source. Okay, this is just a representation, like you can't understand, you do not need to understand this thing. So I hope that you drew this graph in your note, because I'll be taking help of this graph. I actually remember this graph, so I don't need to like go always to this graph. See, what are we actually going to do? We are going to take a Q. Okay, very good. I took a Q, I pushed the source into it. After pushing the source, what you do is you take the frontmost element of Q. Now you might ask, what is Q and what's even a frontmost element of Q? I'm telling you, see, Q means, suppose you go to a cinema hall to buy a ticket. So the guy who goes first to the counter, there is a person, there is another person, and then there are more person. This guy came first, so this guy is going to get out first also. So first in, first out. So if you had like multiple nodes here, suppose 2 3 4, so if I ask you like who is going to get out first, you will say 1. Why? Because 1 came first. Okay, so for now, like as you can like very easily see, we took a Q, we are going to take the frontmost element of the Q. Which one is the frontmost element of Q? 1. So we are going to take 1. Take 1, like take the frontmost element. Wait one second. Yeah, so take the frontmost element, go to its neighbor. Go to its neighbor. do one more thing, like here print it and then go to its neighbor. So take the frontmost element which is 1 and then print it, like take the frontmost element and print it. Suppose this is your terminal, so you printed 1 and then you go to its neighbor and push them also into the queue. Push them also into the queue. So you went to 1, you went to its neighbors, you went to its neighbors. Okay, so one's neighbor is 2 and 5, so we are going to go to 2 and 5 and we are going to push it, but there is a condition. Push it only when those elements are not already present. So we have to push 2 and 5, correct? So before pushing 2, we'll check, is 2 already in the queue? No, so push it. Go to 5, is 5 already in the queue? No, push it. Okay, you understood what I'm trying to say here. After pushing it into the queue, like here you can write, push them into the queue if not already present. If not already present, then you can like push it into the queue. Now what we are going to do, after pushing that element, you have to delete the frontmost element. Okay, after that delete front. Over. This was just the algorithm. Now I'll tell you like how are we, like what are we actually going to do. So let me just explain this algorithm again in a very like short like thing. Take the frontmost element, print it. After printing that element, go to its neighbor, push if already not there, already not present, then push and then delete. What do you need to delete? You need to delete the source node. Okay, like the frontmost element, this element, you can delete this element. If you can like somehow remember this, if you can like just somehow remember this, you are definitely going to get 7 out of 7 marks in BFS. Now we are going to do this. Okay, so what is the first step? You push 1, you take the frontmost element and print it in the terminal. You go to the neighbors of 1. What are the neighbors of 1? 1 2 3 4 and a 5. So what are the neighbor of 1? 2 and 5. Okay, so you go to its neighbor 2, you ask, hey 2, are you already present in the queue? It says no, then you push it. Now you go to the other neighbor which is 5 and then you ask, hey 5, are you already present in the queue? 5 says no bro, I'm not there, so you push it. Okay, now after pushing, what do? You delete the frontmost element, you delete this. After that you do the second same thing again. You go to the frontmost element. Now tell me one thing, what is the frontmost element? 2 is the frontmost element. You go to 2, you print 2. You can, as you can see, like you go to the frontmost element and then you print it. You go to 2, you went to 2, you printed it. Now what do we have to do? We have to go to the neighbors of 2. Who are the neighbors of 2? It is 3, 4 and 1. Now we go to 3, ask, hey 3, are you still present in the queue? Like, are you already present in the queue? It says no bro, I'm not present. So you go and push it. Now you go to 4, you ask, hey 4, are you already present in the queue? It says no, I'm also not present. Then you push it into the queue. Now you go to other neighbor, like 3, 4 are done. Now we are going to go to 1. Okay, now you go to 1, you ask 1, hey 1, are you still present in the queue? It says yes, I am still present in the queue. You might say that we deleted 1, na? Like we dealt with 1, na? Now we don't need to push 1 into this queue. Okay, so we are not going to push 1. Okay, after pushing, you delete this. Okay, now we are going to take the frontmost element. Which is the frontmost element now? 5. You take front, you print front, and then you go to the neighbor of front. What is the neighbor of front? The neighbor of front is 1. You go and say 1, are you already into the queue? it says yes bro, I was at some place, I was into the queue, so you don't push me into the queue again. Okay, after like pushing or not pushing, you delete it. Okay, now you go to the other frontmost element, you say hey 3, I'm going to print you and tell me who are your neighbors. So the neighbor of 3 is 2. You go ask 2, hey 2, are you already in the queue? It says yes bro, I'm already in the queue. So you don't print, you don't push 3, you don't push 2, and you delete 3. Now you take another frontmost element. So this is the frontmost element, you print it, you go to its neighbor, its neighbor is 4, you go to 4, sorry, you go to the neighbor of 4, the neighbor of 4 is 2, you go to 2, you say bro, are you already present in the queue? It says yes, I am already present in the queue. So you say okay, I'm going to delete it. What did we get as our output on the terminal? We got 1 2 5 3 4. What's going to be the BFS output of this graph? You'll say 1 2 3, sorry, 1 2 5 2 5, this is 5, this is 5, and then 3 4, 1 2 5 3 4. You got the same output. This is how you do BFS. Okay, now how will you write the algorithm and everything? I told you, you got it, you can write at least something, you can at least write something. So you just go in the exam and write whatever you understood. Now what is a DFS? So DFS requires something as recursion and backtracking. Recursion and backtracking. We are not going to go into recursion, we are not going to go into backtracking, but I'm going to teach you a trick. So firstly, you need to understand what actually a DFS is. 1 2 3 4 5. So DFS means depth first search. DFS means depth first search. So you go to 1, print 1, you go to the child of 1, the child of 1 is 2. You might say that the child of 1 is 5, so you can go this way also, but like I'm going this way. Okay, so the child of 1 is 2, you went to 2. Now you say I'm also going to go to the child of 2 first. You go to 3, you print 3. Now you'll say that I'll go to the child of 3. There are no child of 3, so you go back. Now you go to the other child of 4, other child of 2, which is 4. You print it. You go to the child of 4 now. The child of 4 is nothing, so you come back. Now after coming back, the first child of 2 was done, which was 3. The second child of 2 was also done, which was 4. Now, are there any more child of 2? There are no more child of 2. So पीछे जाओ. So we go back to 1. Now the first child of 1 is done. The first child of 1 is 2, so 2 is done. So now we go to other child of 1, which is 5, and we print 5. And then we go to the child of 5. There are no child of 5, so we come back. Now what do we do after coming back? We say कि 1 का पहला नोड तो हो गया, पहला चाइल्ड तो हो गया, 1 का second child is also done. Now we have to go to other child of 1. There are no child of 1. So what do we do when there are no child? Like when 5 had no child, we went to the parent. So यहाँ पे भी we can go to the parent, like parent of 1, but there is no parent of 1. That means the DFS is done. The DFS is done. So what did we get as our output? 1 2 3 4 5. Now you might say that the output is sorted, but that's not a condition. Like it's just a coincidence that the output is sorted, because the values of the nodes were in such a way that we got a sorted output. But like it's not important that we are going to get a sorted output here. Now so yeah, as you can see here, we went to the depth, and then like we went up, and then we went like to the siblings. So that's why it is called as depth first search. Okay. Now what's the algorithm? Remember I told you one thing. Wait, let me create some space here. 1 2 3, and then here it is 4, and then here it is 5. I'm going to teach you a trick. This trick is so good that no one can recognize that you don't know DFS. It's just a learning trick of DFS, okay, whatever it is. So what are you actually going to write in the exam? So you'll get a graph. You'll firstly create a adjacency list. After creating the adjacency list, you will say just write what I'm saying just in the exams. Okay, just write it as it is I'm saying. So you'll write, we are going to create a adjacency list, and then you will write the adjacency list. Okay, now you'll write, let's go to the source node of the graph, which is 1. Now from 1 we are going to print 1. After printing 1, we are going to go to the child of 1, that is 2. After going to 2, we are going to print 2. After printing 2, we are going to go to the child of 2, which is 3. After going to 3, we are going to print 3. After printing 3, we are going to go to the child of 3. And as you can see, there are no child of 3. So we are going to go back to the parent of 3, that is 2. After going to the parent of 3, which is 2, we are going to go back to the child of 2, the other child of 2, which is 4, of course. And then after going to 4, we are going to print 4. After printing 4, we are going to see if there are other child of 4. There are no child of 4. So we are going to go to 2 again. Like we are going to go back to 2. After going back to 2, as we can see, all the child of 2 has been processed. So we are going to go to the parent of 2 again. Now we are going to go to parent of 2. Now the first child of 1 has been processed. Now we are going to go to child of 1, that is 5. We go to 5, print it, and then we see that there are no more child of 5. So we come back to 1. And then as we can see, there 1 has no parent. That means 1 is the source node. Source node means parent of parents. Okay, the first guy. So 1 has no parent. That means that is the source node. And once we reach the source node, and then there are no more child to explore, that means we have successfully completed the DFS. So this is just a trick. Write it as I said, in the exam. You will get 7 out of 7 marks. Nobody is going to, actual DFS is also like this only. It's just that we have to write code. So we need to know an algorithm. So the algorithm works in such a way that it goes to 1, and then it goes to 2, and then it goes to 3, and then comes back to 2, and then goes back to 4, and then comes back to 2, and then goes back to 1, and then comes to 5, and then goes to 1. Okay, the algorithm works in such a way. If you know recursion, you might have understood something. If you don't know recursion, no problem. You understood DFS trick. And you'll be able to go through it. Okay, now there are 2 more topics left, and as I promised, we are going to complete it in 40 minutes. I don't think we'll be able to complete it in 40 minutes. 5-10 more extra minute it might take. So the third topic is dijectras. In order to understand dijectra, you have to understand one thing: priority queue. Priority queue. Okay, now there is no need to fear from priority queue. Priority queue is very easy. Okay, in order to understand prims, you have to understand priority queue. So in order to understand dijectras and prims both, you have to understand priority queue. So understand priority queue for one time. After that, you will be sorted with dijectras and prims and everything basically. So I'm going to tell you what's a priority queue actually is. Suppose I have a queue. I push 1 and 0 into it. After that, I also have a queue where I push 0 and 2 into it. After that, I again have a queue where I push 2 and 3 into it. Okay, now if I ask you what is the frontmost element, you will say 1, 0 is the frontmost element, because we have understood that priority queue is also a type of queue only. You will say priority queue is also a type of queue, and queue works on the principle of FIFO. So on the basis of FIFO, you can say that 1 comma 0 is the frontmost element, but that's not the case. Here the frontmost element is the smallest one. Which is the smallest in between these three? You'll say this one. This is the smallest. You'll say how it is smallest? Because see the first element of everything. You know, the first element of this is 2, this is 0, this is 1. So the first element of this one is smallest, na? So 0 comma, what it was, 2. Now I ask you one more question. Suppose I pass 0 comma 2, 0 comma 0, 0 comma 1. Which is the frontmost element here? Now the first element is same, so you go and compare the secondmost element. Secondmost element is this, so this is the frontmost element. I don't know what did I say just now, but yeah, the second smallest element is 0. Like in between 1, 2 and 0, the smallest one is this one only, na? Because this is same, so you can't compare on the basis of the first element. You have to go and compare on the basis of second element. And if you say second element, 0, you know, 1, 0 and 2, the smallest one is, what is smallest in between this? I think I'm like over explaining this, but whatever it is, like the smallest is 0, na? This one had 0, so 0 comma 0 is the smallest, also the frontmost. Now someone who already know priority queue might understand one thing, that priority queue sometimes gives you the maximum element also. That depends. One more thing I was saying, you said priority queue is a type of queue. Is a type of queue. This is not true. Priority queue is a type of heap. Okay, heap. There are two type of heap, max heap and mean heap. The thing that we are going to use in disjecta and prim is a mean heap. You leave everything, like priority queue is like, priority queue means like the element which gives you the minimum element. Yeah, the minimum element. Now disjectas and prim's algorithm, we are going to understand it in just a minute. Okay, just give me a second. Okay, so now we are going to learn what are but I'll give it another sort. You know, you got something like you got 10%, right? If you got 10%, I'm going to give it another sort. 0, 1, 2, 3. Let's do for this graph. Okay, so you push 0 comma 0 into the queue. Okay, now after pushing 0 comma 0 into the queue, you do one thing. You assign an infinity array, 1 2 3, 0 1 2 3. Here you assign 0, infinity, infinity, infinity. You go to 1 1 and wait, just give me a second, 4 and 2. Okay, now you go to the neighbor of 0. You take 0, you go to the neighbor of 0, which is 1. You ask what is the distance. So I'll tell you a formula to calculate the distance. The distance of a node will be distance of its parent from where it is coming plus the weight in between its parent and the node and the current node. If it is better, we'll update the queue, we'll update the array and also the queue. Okay, that is what we are going to do. So let's calculate the distance of 1. Distance of 1 is equal to distance of parent. What is the distance of parent? The distance of parent is 0. The parent is 0 and the distance of parent is also 0. So 0 plus weight in between parent and node. Weight in between parent and node is 3. So we get 3. So distance of 1 is 3, which is better than infinity. So we'll take it and we'll also push it. Wait. We'll push the distance also into the queue. So what are we actually going to push? We are going to push the distance and then the node. Okay, and this has been updated to 3. Okay, this has been updated to 3. Now we go to the other node, the other child. We go to 2. How are we going to calculate distance? Distance of parent, which is 0, plus the distance of the weight in between parent and the node, it is 1. So the distance comes out to be 1. So the distance comes out to be 1, which is better than infinity. So we are going to update the matrix and also push it. What are we going to push? We are going to push the distance, which is 1, and the node, which is 2. Okay, now I ask you a simple question. What is the frontmost element of the priority queue? You'll say it is 1, 2. Okay, so let me just draw it again. The queue looks like, the frontmost element is 1, 2, and then 3, 1 is also there. 0, 0 has been deleted. The array looks like this: 2, 3, 0, 4, 0, 1 here and 3 here and infinity here. Okay, now we go to 1. We ask, who are your neighbors? So it says 0 and 3. Now let's calculate the distance for 0. What did I tell you? The distance for 0 is going to be the distance of parent. The distance of parent. What is the parent? For now the parent is 1, because we are coming via 1. Sorry. 1, 2 means 2 is the node. So we are coming via 2. So the parent is 2. The distance of parent is 1. The distance of parent is 1. We updated it, na? And then the weight is 1. So 1 plus 1 is 2. So the distance of 0 is 2. Is it better than the previous distance? The previous distance is 0. No. So we are not going to take it. Okay. Now the other child of 2 is 3, right? So we are going to take the distance of 3. The distance of 3 is going to be distance of parent. Distance of parent is like distance of 2. Distance of 2 is 1 plus the weight in between 2 and 3, 2. So 1 plus 2 is 3. So we get the distance of 3 as 3, right? Is it better than the previous one? Let's see. Yes, it is better than the previous one. So we have stored 3. And when you are changing the array, you also need to change the priority queue. You have to pass the distance and the node into the priority queue. So we pass 3, 3. Now this is done. We are going to go to other iteration. This is 3, 1. 3, 1. Okay, now we go to 3, 1. What is the node? 1. And what's the distance? It is 3. So from 1, where can we go? We can go to 0. From 1, where can we go? We can go to 3. So let's calculate the distance of 0. Distance of 0 is going to be distance of parent. Distance of parent is 3 plus the weight in between 0 and 1, which is 3. So 6. Is 6 better than the previous distance? No. So we are not going to update it. Now we go to 3. Distance of 3 is going to be the distance of parent, which is 3, and the distance in between 3 and 1. It is 4. So we get 7. Is 7 better than the previous distance of 3? The previous distance of 3 was what? 3. We updated it, na? We updated it to 3. Now we are calculating the new distance is 7. So 7 is not better than 3. 3 is better. So we will not change it. We did not change it. So if we did not change it, we are not going to push anything into the queue. So this is also done. Now the last one is 3, 3. Last one, 3, 3. Okay. 3, 3. The node is 3. From where we can go from 3? We can go to 1. We can go to 2. So distance of 1 will be distance of parent. What is the distance of parent? It's 3. What is the weight in between 1 and 3? The weight in between 1 and 3 is 4. So we get 7. Is 7 better than the previous distance of 1? The previous distance of 1 was what? 3. So no, it is not better. So if it is not better, we will not take it. So distance of 1 will not be taken. What about distance of 3? 2. Distance of 2 is going to be the distance of parent. Parent is 3. The distance in between 2 and 3. The weight in between 2 and 3. The weight in between 2 and 3 is 2. So 5. You can see these things in the graph. Like you can see, like distance of parent means parent of 2 here is 3. Okay, and distance is 3. Okay, so 5 is 5 better than the previous distance of 2. What is the previous distance of 2? Previous distance of 2 is 1, so it is not better. So we are not going to update the array, and also we are not going to change the queue. So if we'll not change the queue, this is also done. So the queue is over. So the queue is what? Over. So when the queue is over, the final matrix that we got, the final matrix or the array that we got was this 0 3 1 3. Let us just write it. 0 3 1 3. Now this is the distance. What does it represent? The distance in between 0 and 1 is 3. The distance in between 0 and 2, shortest distance in between 0 and 2 is 1. The shortest distance in between 0 and 3 is 3. Let's see in this graph. Are we getting a correct output? 2 and a 3. Okay. Here it was 3. Here it was 1. Here it was 4. Here it was 2. Okay. So here, as you can very easily see, the shortest distance from 0 to 1 is 3 only. So this is correct. The shortest distance between 0 and 0 is 0 only. So this is also correct. The shortest distance between 0 and 2 is 1 only. You are not going to go via this path, right? This is not good. So it is 1 only. This is also correct. What about distance of 3? So distance of 3 was 3 plus 4, 7, and 1 plus 2, 3. 3 is better. So 3 came out here. So this is a correct output. So I wasted 10 minutes while trying to explain disjectras, taking a very long graph, because like last time the graph was long. So I was saying, sorry, the recording got cancelled. I don't know, there is a setting in my mobile phone which cancels the recording after 1 hour. So I'm sorry. So I was saying that there are some things in life that is very easy to understand by yourself, and there are something in life where you need someone else help to understand it. Disjectra is one of those topics that you can understand by yourself only if you give your efforts. But I tried my best. If you did not understood, I'm sorry. I kind of took the big graph, so which is very hard to digest on the first go. That's the reason you might have not got the real intuition behind disjectras. But on the second time when I took this graph, 1 2 and then a 3, you must have understood it. Okay. So now the last topic. I'll not take more than prims. For prims it will not take more than 10 minutes. I'm sorry, I kind of promised I'll take 40 minutes, but I took more than 1 hour. I'm sorry. Okay, now the next topic is prims algorithm. So in order to understand prims algorithm, you have to understand what a MST is. Okay, I'll tell you what MST actually is. 0 is connected to 1, 1 is connected to 3, 3 is connected to 4, 4 is connected to 1 is connected to 2. There are some weight that I'm going to assign to these things. Okay, 2, it is 2. Tell me the number of vertices here. You'll say 5. 1 2 3 4 5. 5. Tell me the number of edges. 1 2 3 4. What? Oh shit. I'm going to draw some more edges. 6. And I'll draw one more edge here. 7. Okay. So the number of edges are 6. The number of edges is 6. So MST means if the number of vertices are n, then the number of edges should be n minus 1. This is as simple as it gets. So here are 6 edges for 5 vertices, which we need to make 4 edges in 5 vertices. So we have to remove 2 edges. Okay. So there is a rule that is there when you have to remove edges. What's that rule? The rule says that you can only remove edges in such a manner that their is a path from one node to other node. Like just you have to remove two node, na? Suppose you remove this node and you remove this node. Now is there a, you remove both the nodes, okay, both the edges. So is there a path from 0 to 1? No. Is there a path from 3 to 1? No. So this graph got disconnected. This graph got disconnected from this graph. Did not want this, right? We just did not want this. So you understood one thing here, that you cannot remove like edges in such a way that you disconnect the graph. But suppose if I remove this edge, if I remove this edge, okay, will my graph be affected? You'll say no, you can still reach 1 via 3 and 0. You know, from 3 you can reach 1 via 0. So there is a path. So we'll remove this edge, okay, because this is not affecting. Now you might say that you could have also removed this edge and not this. Like you might have said that we could have also removed this, because after removing this you can also, you can go to any node, you know, you can go to 0 via 3 from this way. So but removing this node is always a better option. You cannot remove both, I told you why, but you can remove one of them. So which one will you remove, this one or this one? You'll say this one I'll remove. Why? Because this gets my sum to sum more lower. Like if you find out the sum of weights of the total graph, if you remove this one, the sum will decrease by 8. If you remove this one, the sum will decrease by 2. So we don't, like, we want the sum to remove by the maximum magnitude. So we did that, okay. Okay, so now you removed 2. Now what do you want? So we removed, so you removed 8. Now you can also remove this one. You might say that I could have removed this 5 also, but understand this, na, removing this is a better option because the magnitude is 7, you know. So we'll remove this, okay. So let's just remove these two nodes and see what the sum comes out to be. Okay, wait. Need to take the ink and then go here, come to brush, and then we'll remove this one edge and then we'll also remove this one, okay. So now take the ink. What is the sum, total sum? 6 plus 2 8 plus 5 13 plus 3 16. So if you can somehow get other graph, so other ways to remove the edge so that the sum is smaller than 16, then that will be MST. But for now this is only the MST. You basically, you can try, you will not get sum lesser than 16, you know. So now as you can see, this graph has 5 edges, 1 2 3 4 5, and this graph has 1 2 3 4 edges, 5 vertices and 4 edges. Sorry, I'm fumbling a little bit now. So this is a MST. This is a spanning tree, okay. This is a spanning tree, and if the sum is minimum, then it's a MST, means minimum spanning tree, okay. So I just hope that you got it, you got the real intuition behind it. Now let's try to understand the Prim's algorithm via other graph, okay. We'll take other graph, 0 1 2, and then there is another 4, and then there is 3, okay. So 1 2 2 1 2 and 1. So what does a Prim's algorithm actually is? So I ask you one thing, what was BFS? BFS was what does actually BFS, what was BFS? You push the source node and then you take the front, and then you print it, and then you go to neighbor, push it into the queue, and then delete the front. This was BFS. Just change one thing, we are pushing in, like in place of queue, just take priority queue here, just take priority queue, and there we were pushing just the node. In BFS we are pushing just the node. Here we are going to push the wait, node and the parent. Okay, and nothing changes. Okay, so I want you to do one thing. Again, draw this graph. Okay, draw this graph. I also drew this graph on my copy. You draw this graph. Once you have drawn this graph, I'll tell you how does the prims actually going to work. It's a very easy algorithm. So at first you push 0, 0, -1. Okay, just push it. Okay, take this. Now you go to the you go to the neighbors of 0. You go to the neighbors of 0. Who are the neighbors of 0? 1 and 2. Okay, so you go to 1 and you push the weight which is 1, the node. So you go to 2, you push the weight which is 1, the node which is 2, and the parent of 1, parent of 2 which is 0. Okay, so you push 1, 2, 0. Remember to push the weight firstly. Okay, after that you go to 1. The weight of the weight in between 0 and 1 is what? 2. The node is 1, the parent is 0. So you pushed it. Okay, now you delete it. Okay, and also initialize a sum variable from 0. Now you will take this one, right? This one, because this is the frontmost element of the priority queue. Now you took 1, 2, 0. Okay, you say sum will be 0, the previous sum plus now what did you get? 0. So you say the sum now is 1. Okay, the sum now is 1. Now you go to the neighbors of 2. Who are the neighbors of 2? They are 1 and 4. So you go to 1. Okay, so you go to 1 and you try to push 1 into the priority queue now. Okay, so you push 1 into the priority queue. The parent is 2, and what's the weight while between 2 and 1? What's the weight in between 2 and 1? It is 1. So you push this, and then you'll the other neighbor of what? 2 is, the other neighbor of 2 is 4. So you push 4, the parent is 2, and then the weight in between the node and the parent is 2. The weight in between 4 and 2 is 2. Okay, so we'll push this one and this one. Okay, wait, shit, oh shit. Okay, so we'll push it into the priority queue. So 0, 0, 1 was done. This is also done now. So 2, 1, 0 is left, and then we are going to push these two nodes, 1, 1, 2 and 2, 4, 2. Now you take 1, 1, 2, because this is the frontmost element in the priority queue. 1, 1, 2. The sum till now was, the sum was 1. So now the sum will become 1 plus the new weight 2. Okay, the sum becomes 2. 1, 1, 2 is the priority queue's frontmost element. So we take 1. Okay, so we take the node and then we say who are your neighbors. The neighbor is 0 and 2. Okay, and then you push the weight in between 0 and 1. The weight in between 0 and 1 is 2, and then you push the node which is 0, and then you push the parent which is 1. And then with respect to this, you are going to push the node and the parent and the weight in between 2 and 1. The weight in between 2 and 1 is 1. So you push these two things and then you delete it. Okay, so you push 2, 0, 1, 1, 2, 1. Just give me a second. Delete it. Okay. Okay. So we'll push. We'll push 2, 0, 1, and we'll push 1, 2, 1. Now again, what is the priority queue's frontmost element? This one, 1, 2, 1. So 1, 2, 1. Okay. 1 comma 2 comma 1 is the frontmost element of the priority queue, right? So now we are going to take this one. Okay. So 1 comma 2 comma 1. Okay, so now you can go to the neighbor of 2, you can go to the neighbor of the other neighbor of 2, you can do the same thing, you can change the sum. The sum will be, the sum before was 2, the sum now is 2 plus 1, it's 3. Okay, so you can change the sum also. You can go to the other neighbors of 2, you can change the sum also. So at last, after 4 iteration, like after 4 iteration, you will get no, yeah, after that like after 6 iteration, actually, to be honest, like after 6 iteration you will get it. After 6 iteration, so we have to do this thing for 6 time, like 6 time you will get a value of sum. The value of sum that you will get now, that is the value of sum of MST. So this was the algorithm. So you don't have to like write the full algorithm, you can write it and then you can like just go away from it. So how are we actually going to write the algorithm of prims? So what were we doing? We took a priority queue, we had a source node, we went to the source node, updated sum, that was the first step. After that we pushed the information of their neighbors, and then the third step was delete. So the thing is S and D, sum, neighbor, delete. This is Prim's algorithm. Okay, now if you understood 10%, go and write it, you'll get 5 to 6 marks. Okay, I'll make another video where I'll actually teach the Prim's algorithm when I probably will have the iPad, like I'm trying to buy one. So after I get the iPad, I'll teach Prim's algorithm and also the code of these things. So for now, let's keep it like till here only. I took 1 hour 15 minutes, just little bit lesser than what I promised, like little bit lesser than the double of what I promised. Like I promised 40 minutes, I took 1 hour 15 minutes. I'm sorry, but like you'll get like out of 7 marks you'll at least get 5 to like 6 marks if you write it in a good way. If you have the skill of writing, then you'll get 7 marks, 7 out of 7 marks in graph chapter tomorrow, like in your exam. So tomorrow or whenever your exam is, this is like too much to study in graph, and graph is a tough topic. So I tried to keep it like as simple as it could have been. So thank you guys, and one more thing, thank you. And you can like if you want to like, if you found it helpful, you can like it, you can subscribe it. One more thing, this was the first video that I made on YouTube, so I might have like fucked up a little bit. So if I did that, you can comment it out what I can actually improve. I know screen is a problem, so I can definitely improve on screen, but other improvement, any other improvement if you want me to do, you can tell me. Okay, so thank you.